Okay, the last thing for this week is I'm going to introduce you to the idea of a series. Series just means sum. So let's say I have a sequence. Remember, a sequence is a list of values, but I'm going to add every single term in my sequence together. That would turn it into a sum, which we would refer to as a series. So in this example, I'm just adding up the first n natural numbers. You might have seen a trick for how you can figure out this sum. Let's call it S. This is attributed to the young mathematician Gauss. There's a maybe apocryphal story here, which is he was in kindergarten, first grade. Choose whatever young age you want, because the story may not be true. And he was causing trouble, and so his teacher said, Gauss, because she always referred to him by his last name. She said, Gauss, Carl Friedrich, go into the corner and add up the first 100 numbers. And then come back. And she was imagining that he's going to, take a while to do this and he'll be out of her hair. But he comes back, 30 seconds later with a correct answer. How did he do it? So the way the story goes is he noticed this pattern. 98, 99, 100. So this is the sum he was being asked to do. Rather than just adding it straight forward this way, he noticed 1 plus 100 is 101. And 2 plus 99 is also 101. And 3 and 98 is also 101. And if you think about how many of these pairs there are, there's going to be 50 of those pairs. So 101 times 50 is the same thing as 101 times 10 times 5. So this part's easy to do in your head. That's 1010 times 5. Instead of multiplying, you could probably multiply out by 5 longhand, but you could also think about it this way. 1010 times 10 divided by 2, because that's the same thing as multiplying by 5. It would be multiplying by 10 and then dividing by 2. And so this would give us 10,100 divided by 2, like that. So the way I think about what this is 10,100. So let's think about it literally as 10,000 plus 100 divided by 2. Whoop. So then 10,000 over 2 is 5,000. And then 100 divided by 2 is 50. So the answer should be 50/50. And you could have done all this stuff in your head. There's no long algorithms that you have to follow to do it. So that's kind of a neat idea. I'm going to show you a different version of the Gauss trick here. Because, some people might wonder, well, what happens? This worked because there was an even number of numbers in this list. And so every number had a matching number. But what would happen if we went up to 101? Then you'd have a central number that wouldn't have a match. And so, does the same trick work? The answer is yes, but you'd have to kind of think about these two separate cases separately. What if there's an even number of terms? What if there's an odd number of terms? So I'm going to show you what's essentially the exact same trick, except I'm going to do it in a way that makes it where we're going to treat all of the cases the same. And we're also going to do it in general. So let's say that we're going up here to n minus 1 and then n. So I've got a series that starts at 1 and then goes up to n. I'm going to write the series twice, except the second time I'm going to write it backwards. Whoops. So n minus 1, and then here's 2, and then here's 1. And now I'm going to add both of these equations together. So on the left-hand side, this entire sum equals S. This entire sum is also equal to S because the order doesn't matter. Just because I wrote it backwards doesn't mean the total number is changing. So on the left-hand side here, I have 2S. What do I get on the right-hand side? Well, 1 plus n is n plus 1. And then 2 plus n minus 1 is also n plus 1. And I hope you see that in this sum, whenever I go from one term to the next, I'm adding one number. In this sum, whenever I go from one term to the next, I'm subtracting a number. So if I'm adding down the columns here, if this column equaled n plus 1, the next column should be the same thing because I added 1 and also subtracted 1 from the total column. So those balance out. So what that tells us is that every single column here is adding to n plus 1. And then you can ask, well, okay, how many of these n plus 1s are there? And in this case, if you look at how many terms there are, there's just n terms because I'm going from 1 up to n. So rather than write it out as a sum, I can say there are n of the n plus 1s because I have n plus 1 n times. So now we have a nice equation for s. S is n times n plus 1 over 2. We have derived it. Okay, what I want you to do right now is try and do the same thing. Try this. Try to do the same approach for 53 up to 105. So if I wanted to use the Gauss approach, and this is not the only approach, we'll look at another one in a second. We'd have 105, 104, 103, blah, down to 53. So we're going to add it up. We'll have 2s equals, let's see, this is 158. And we have 158 a whole bunch of times. How many times? Let's see, we have to figure out how many things we're adding up to get from here to there. I'm tempted to say, let's do this. Let's say 105 minus 53 is 52. So I'm tempted to say there's 52 terms here, but let's make sure that this way of calculating the number of terms makes sense. Because like this is too big for me to think about. So let's check the same approach with a smaller sequence. So let's say it was just 53 to 54. If I want to know how many terms is that, like with my eyeballs, I can see it's 2 terms. Let's do the same calculation approach. I'd have 54 minus 53 would give me 1, but clearly there are 2 terms here. So what that tells me is that taking your last term and subtracting your first term is going to give you a number that is 1 smaller than the actual number of terms. So I think this doesn't make sense. I think the true number is 53 terms, which is interesting. All right, so what does that give me? I've got 158 53 times. I'll divide both sides by 2, and so now I know what S is. S is 158 times 53 divided by 2. So that's one way you could have done it. Let's do it a different way. So if I want to know the sum from 53 to 105, I could just find the sum starting from 1 all the way up to 105, and then subtract this part, subtract the sum from 1 up to 52, and what I have left over is this part here. So if you remember our equation from last time, we had the sum of the first n terms from 1 to n was n times n plus 1 over 2. So if I wanted to, I have too many s's here. Let's call this SP, and let's call this nothing at all. Okay. So if I wanted to find out what this partial sum is, the SP, what I could do is I could apply this equation up to 105. So I'd have 105 times 106 over 2. So now I know this is equal to the sum from 1 to 105. And then I would subtract the sum up to 52, which would be 52 times 53 over 2. And like, yay, I'm done. All I'd have to do is figure out what that number is, but like I've solved it. So what are you supposed to take away from this? I'm trying to show you how to think flexibly because I'm going to give you different problems where you might need to use one method, you might need to use another method. So don't feel like you need to slavishly practice one approach. That's not the point. The point is to try and develop flexible thinking about what could you do with these sums.